Welcome to fourth GATE class in the subject of fluid mechanics and turbines. So in the last class, we have solved so many problems in the fluid statics. Now one more problem in the fluid statics we have to solve here and then continue the kinematics and differential fluid flow analysis. A hinged gate of length 5 meter inclined at 30° with a horizontal and with water mass on its left. That is shown here. The density of water is 1000 kg per meter cube. The minimum mass of the gate in kg per unit width perpendicular to the plane of the paper. So record to keep it closed is what? The option given is ABC, some values. Here, this must be kept closed. So the torque generated by the weight of the fluid must be equivalent to the torque generated by the plate. So the given values, that is, if you're taking the gate at a particular point, that is, you can take some differential element from the hinge to this differential element. The distance is S. So here, the middle, you have some weight. This may be exactly at L/2 level. But in the gate, at a differential element at a distance of S, the pressure is acting. The torque due to pressure of water equal to torque due to weight of the plate. So the pressure created here. So in this condition, here on a S, so this angle is 30. So there's a 30°. So if you're taking this height at a particular S value, this is given by S into sine theta. S into sine theta. Then the torque due to pressure of weight equal to, now that rho g, here the y value is S sine theta, then the differential element into the distance S. This is a torque due to pressure of water. Then if you're substituting this thing rho g, then y equal to S sine theta into ds. Yes, if you are rearranging, you can get rho g S square sine theta ds. Or in the aligned one, you have rho g sine theta into S square ds. This is for a small infinitesimal element. If you are getting an overall length of the plate, the torque equal to integral 0 to over 0 to L and rho g sine theta s square ds is equivalent to what? The torque due to weight of the plate. The torque due to weight of the plate is, so this length is L, at the middle the weight is acting. So the middle the weight is acting. This is 30°. So if you are drawn this here, this will be a 30°. From the hinge, the vertical, this distance equal to, this is L by 2. So this one is L by 2 cos theta. So the torque produced by the weight of the plate equal to mg L by 2 cos theta. So this value equal to mg L by 2 cos theta. If you are integrating this, you can get rho g sine theta s cubed by 3 is equal to mg L by 2 cos theta. So here the g will be cancelled. So the m equal to 2 by 3 rho sin theta divided by cos theta. You can get tan theta. Then here over the length we are integrating, so the s become L. So this L, one L will be cancelled, again one is L square. So the 2 by 3 rho L square tan theta is the weight required to keep the plate as a closed one. If you are substituting the value of density, the density is 1000 and the L is 5, so 5 square tan theta is 30. So the value will some 9623 kg. So this is the answer for the first particular question. So next I have to go for a fluid kinematics and differential analysis of fluid flow. Here the representation of fluid particles or fluid domain is in the form of differential or in an algebraic form. So here the fluid kinetics is a study of how fluid flows and how to describe the fluid motions. So I have two types of description. One is a Lagrangian description, another one is a Eulerian description. The Lagrangian description, the position of any fluid particle is represented by the position vector as well as the velocity vector. So using this one, we can track the particle or the fluid matters. The Eulerian description, fluid flow, a finite volume is called a fluid domain or a control volume, which is defined through the fluid flow in and out. Instead of tracking individual fluid particles in the previous cases, okay, we can consider a fluid domain that is represented in terms of space and time. Okay, if you are taking the pressure field is given by x, y, z, and time. Velocity also represented by velocity vector is given by x, y, that is a space coordinate, and the time coordinate. Acceleration field also represented by an ax, y, z. If you are taking the acceleration in the sense, the total acceleration is given by the acceleration in x direction, y direction, and z direction. So acceleration in each direction is vary. That is, ax is a suffix as x is vary, a suffix y is vary. Similarly, velocity field you have a each direction you have a different velocities. The final one represented in terms of the unit vectors of I, j, k. I represent the x parameter. Suppose if you are representing the velocity, there is a velocity of x direction. The I vector represents the x directional quantity. It may be acceleration in the sense there is an acceleration ax represented. So small example is given here. The velocity vector is represented by 0.5 plus 0.8 x I vector plus 1.5 minus 0.y j vector. So here the stagnation point is asked. The stagnation point is what in the sense the velocity at that point is 0. It's a velocity vector. The velocity vector is represented by the combination of all the directional velocity. That is u velocity. This represents the velocity at x direction. Then the v velocity, there is an representing velocity at y direction. Y direction. Here x is missing. Bracket also missing. So the w represents the z direction velocity. So the given equation having only u and v, because the question itself it mentioned two-dimensional velocity field. U value is 0.5 plus 0.8 x and v value is 1.5 minus 0.8 y. So the stagnation point is the velocity component is 0 at that point. So if you are equating this equal to 0, you can get x equal to minus 0.625 meter, y equal to 1.87 meter. The Newton's second law is equal to force equal to mass into acceleration. The force is a vector quantity. Here the mass is scalar and the acceleration is obviously vector quantity. Now acceleration of a fluid particle is given by the velocity vector, rate of change of velocity vector. So here the velocity field is given, is varying from reference frame to a particular time frame. At t time it may occupy some place and then t plus t time it may occupy the another. This position wise x, y, z coordinate wise the changes may be available. Similarly, the time wise the velocity also changing. Similarly, the acceleration also going to change. So the acceleration of the particle is given by dv vector by dt. So the dv vector by dt is given by, there is a function of, the v is a function of x, comma y, comma z, comma t. So if you're putting that one, dou v by dou x into dx, dou v by dou y into dy, dou v by dou z dz, dou v by dou t into dt. Then if you are having a rate of change of this velocity with time, all the quantities divided by time, dt, then you can get here dou v by dou t. Here dt by dt is nothing but u. Here dy by dt is nothing but b, small b. dz by dt is nothing but a small w. So the velocity of a particle is given, so acceleration of the particle is given by dv vector by dt equal to dou v vector by dou t plus u dou v vector by dou x plus b dou v vector by dou y plus w dou v vector by dou z. So acceleration of a fluid particle is expressed in a field variables also. The same thing is represented by dou v vector by dou t plus v vector dot del operator vector into v vector. The gradient or a gradient operator or a del operator is the del operator is represented by I vector dou by dou x plus j vector dou by dou y plus k vector dou by dou z. Suppose the del square, that is in a Laplace operator, that's dou square by dou x, dou square by dou y, dou square by dou z. Here, the dou v by dou t terms, this term is called a local acceleration and is non-zero only for an unsteady flow. So this is a local acceleration. Depending upon time is varying. Then the remaining things are said to be an advective acceleration or a convective acceleration. So this term can be non-zero even for a steady flow. Though dou v by dou t may be zero for a steady flow, but the advective or a convective acceleration is not zero for a steady flow. So the same thing may be represented by a material derivative. Material derivative is capital D by dt. So the Lagrangian and Eulerian things will be merged using this one. So that's given by dou t into v vector into del operator vector. So if you are applying here acceleration or a velocity, we can get dv vector by dt equal to dv vector by dt equal to dou v vector by dou t into v vector dot del operator vector into the same v vector, whatever the things. Similarly, acceleration also we can material derivative of pressure also we can use that dp by dt that's equal to dou p by dou t into v vector dot del operator vector v vector. So here the same problem, the previous problem is taken for an example. For this one, u is given, b is given. You have to find out the acceleration, total acceleration, or the acceleration in x and y directions. So for a x, dou u by dou t plus u dou u by dou x plus b dou u by dou y plus w dou u by dou z. Suppose a y in the sense this is dou v by dou t, u dou v by dou x, b dou v by dou y plus w dou v by dou z. Suppose a z in the sense, a suffix z in the sense, you have a dou w by dou t plus u plus dou w by dou x, b dou w by dou y, like that. So if you are applying these things here, the dou u by dou t, because it's a steady, the time component is not available, this becomes a 0. Then u is given dou u by dou x here 0.8. So this quantity multiplied by 0.8. Then v is given dou u by dou y, because here there is no y component, so this is 0. And then as usual w is 0, so the remaining thing is ax is 4. Then ay is similarly have to here this value u into dou u by dou x. Here there is no y term, there is a b term, so dou v by dou x that's equal to 0. Then b into dou v by dou y, this is minus 0.8, this v into minus 0.8, that's an ax and ay. Suppose the question is asked at a particular point, what is the acceleration? I have to substitute the x and y value in the equation, so you can get the ax equal to 1.68 meter per second square, ay is 0.72 meter per second square. The streamline is a curve that is everywhere tangent to the instantaneous local velocity. So there's a tangent curve, there's a local velocity based. The equation is given by dr by v equal to dx by u or dy by v or dz by w. The streamline in the xy plane is given by dy by dx equal to v by u. The stream tube consists of a bundle of streamlines. So each one is a streamline. The bundle of streamlines are said to be in a stream tubes. The path line is an actual path traveled by an individual fluid particle over some period. As t equal to 0, t equal to 1, and t equal to t end. So it's following some path. You have to trace the path as a path line. So for a steady flow, path lines are identical to streamline. Then the streamlines are converging in the sense flow will be accelerated, diverging in the sense the flow will be decelerated. The straight line is the locus of fluid particles that have passed sequentially through a prescribed point in the flow. That is a straight line. Here the dye is injected, is following a sequential points. If the flow is steady, streamlines, path line, and straight lines are identical. Timeline is a set of adjacent fluid particles that are marked at the same instant in time. So for the particular time, all the particles are in the straight line. Then goes on, what happens the plate, upper plate and lower plate have a viscous effect. So the particle will be sticky, not ready to move us with the previous or middle particles. So this will be in the position. So other will be moving like this. The other will be moving like this. If you are placing that point, you can get a timeline. The profile plot indicates how the value of scalar property varies along some desired direction in the flow field. The vector plot is an array of arrows indicating the magnitude and direction of a vector property at an instant in time. The contour plot shows curves of constant values of a scalar property at an instant in time. So here the fluid may go on translation, rotation, linear strain, and shear strain. Each cases the rotational vector is given by 1 by 2 dou w by dou y minus dou v by dou z plus 1 by 2 dou u by dou z minus dou w by dou x. This alternatively, the I component in the sense I will be removed and the opposite will be in the subtracting terms. Similarly, the linear strain is given by dou u by dou x, the particular velocity along with the axis derivatives, particular then the y velocity and the y derivatives, dou v by dou y. Volumetric strain rate in Cartesian coordinate, that is 1 by v dv by dt, this is given by the summation of linear strain. The shear strain is given by sigma xy equal to, let's say epsilon xy equal to 1 by 2 dou u by dou y plus dou v by dou x. That's other things alternatively have a value of vorticity. Vorticity is a measure of rotation of a fluid particle. Vorticity is equal to twice the angular velocity of a particle. So vorticity vector equal to zeta equal to del vector into v vector, that is curl of velocity vector. The rate of rotation vector, omega vector, is already seen in here. The omega vector is equal to half of the vorticity vector. So vorticity vector at a flow field is non-zero. The fluid particle that happens to occupy that points in space is rotating. That's non-zero in the sense it's rotating. The flow of this rotational. Likewise, in the vorticity region of the flow is zero. Fluid particles that are not rotating, the flow in that region is called the rotational. So here the graphical representation, the pictorial representations of rotations. The bottom, the particular shape goes on rotating along the flow directions. The top is now rotating things. The top, the particular shape is moving along the flow direction but not rotating. The shape is maintained as usual. That is it is a circular or a rectangle. The top eyes are like the eyes at the top in the sense it's keep on the top positions. So based on these small questions may be used for the same problem. The rate of translation, the translation is the same thing whatever the u velocity and v velocity is given. Translation, suppose the point xy is given, if you are putting that one at a particular point, what is the velocity? The rate of rotation, here the two-dimensional problem xy dimension alone. So the rotation is in the z directions. So the rotation vector is given by 1 by 2 dou v by dou x minus dou u by dou z k vector. So if you are differentiating this thing with respect to x by the v velocity and u with respect to y, there is no y component, this is 0, there is no x component, this is 0. So the rate of rotation is 0. Similarly, linear strain dou u by dou x, dou v by dou y. Already dou w by dou z is already 0. That is, there is no w in the component. So you can find out the linear strain using this one. And the shear strain is the combination of this one. Epsilon xy equal to 1 by 2 dou u by dou y plus dou v by dou x. The volumetric strain is summation of all the three. Here, epsilon x equal to 0.8, epsilon y is minus 0.8. If you are adding these things plus 0, the final volumetric strain is 0. The differential equation of a fluid motion, that is here, the previous things what we are taking, that the particular fluid particle will be tracked are the inlet condition and outlet conditions of control volume concept. Inlet and outlet conditions are analyzed. What happened within the control volume, we don't know. In the differential analysis, within the domain also, each and every space we can analyze. That is not differential analysis. In that one, the conservation of mass and momentum equations, then Newton's second law is used. In the differential analysis, all the details of the flow are solved at every point within the flow domain. For a three-dimensional incompressible flow, there are four unknowns. The velocity components u, v, w, that is x, y, z directional component, and pressure. Suppose the four equations are available, four unknowns are available, that will be easily solved. There is no issues. That is the four equations readily available. So one is conservation of mass, the another three is the Newton second law, that is the momentum equation, that is based on the force balancing. Sometimes all the variables are coupled, in the sense you have to solve all the equations simultaneously. The equations are coupled, meaning that some of the variables appear in all four equations. The set of differential equations must therefore be solved simultaneously for all four unknowns. So there is the happen. Now for a small differential domain, what is a mass in? That is the conservation of, that is, if you want to do the conservation of mass, that is the rate of change of mass equal to mass in minus mass out. Rate of mass in minus rate of mass in. So here for a particular small differential control volume, that is volume is dx, dy, dz. The one side you have on the left side is, here you have on mass flow in equal to rho u into this area, you are getting a mass flow rate minus a small differential amount, either in or out, leaving or adding. Here leaving in the sense minus dou u by dou x into d by 2, the vertical one, that is the half way, it's a direction of dx of v, that is here the dx by 2, dx by 2. Similarly, other phases also you can write for that one. Here the opposite direction, if you are going this, here this will be plus dou u by dou rho u by dou x dx by t into dx into dy. Similarly, all the things you have to sum, you can get the mass in, summation of mass. Similarly, the mass out also you can write. The net will be a equation of mass balancing. That is giving a Cartesian coordinate in terms of continuity equation. That is dou rho by dou t plus dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z is equal to 0 for a net. 1 is 0. So the alternative form you can write in the terms of del operator, that is the material derivatives dou p by dou rho by dou t plus del operator dot rho v vector equal to dou rho by dou t plus v vector dot del vector rho. This is material derivatives. Then rho into del operator vector into v vector. So simply continuity equation is represented by 1 by rho d rho by dt plus del operator vector dot v vector equal to 0. For a steady condition, the divergence of, suppose the incompressible fluid, in the sense the rho is a constant, the divergence of vector equal to 0. That is now steady continuity equations. Incompressible continuity equation del vector dot beta. That is, this is removed because it's an incompressible, rho is a constant. Then a stream function is used for representing velocity in the x and y direction in the different manner. There's an incompressible two-dimensional stream function in Cartesian coordinate u equal to tau psi by y. The psi is a stream function, v is minus tau psi by dou x. If you are substituting in the continuity equation, tau square. Substituting in the continuity equations, you can get dou square psi by dou x dou y minus dou square psi by dou y dou x equal to 0. So along the streamline, dy by dx equal to v by u, otherwise minus b dx plus u dy equal to 0. That is, here you have a value of dou psi by dou x. The total change of psi is given by, that is, the psi is a function of x and y only. So the psi function is x comma y, in the sense you have to differentiate by dou psi by dou x dx plus dou psi by dou y dy. The differential linear momentum equation or Cauchy equation is given by, there's a force on over the control volume based on the gravitational forces, then the surface forces, the sigma I j. That is, here it may be sigma x y x x sigma x x sigma y y, like that. The sorting in the surface things. The summation is given by these things. If you are representing in the vector materials, we can get this. One, the special case of flow with well-defined inlets and outlets, it will be replaced by the momentum flux correction factor beta. So the same thing is represented in momentum correction factor. Finally, the Cauchy equation is given by dou by dou t rho v vector plus del operator vector dot rho v vector into v vector. This is given by the force due to weight or gravitational things in del operator vector dot sigma I j. For the same cases, mass balancing conservation, here the momentum, the force balancing is considered for a small element dx dy dz. So the mass term is just multiplied by the concerned directional velocity u. The previous cases you have rho u minus dou rho u by dou x dx by 2 dy dz. Instead of that one, you have another velocity. Similarly, in the vertical direction, thus represent y having a elastic component of V, that is B, then the additional velocity U, because this is considered for an x momentum, so all the terms will be multiplied by the x directional velocity. The rate of change of x momentum within the control volume is given by over the control volume dou by dou t rho u dv. The dv is a volume change. The x momentum in particular x direction is given by dou rho u by dou t. Similarly, in the continuity equations, here u is coming, then another u, then u, that is additional u instead of the v. Similarly, y direction in the sense you can get a v terms in all the multiplications. That's equivalent to the gravitational force, then the body surface forces sigma dou sigma xx by dou x. Then here there is an x momentum equation. The x with y direction, x with z direction is what that force is mentioned. Similarly, in the other cases, the y direction, the forces in y direction with x is what? Sigma xy. Then the forces in the z direction is what? Sigma yy is in the same surface. Similarly, z directional things. In an irrotational region of flow, the velocity vector can be expressed as a gradient of a scalar function, that is called a velocity potential function. So applies to any orthogonal coordinate system as long as phi is a smooth function. In other words, if curl of a vector is 0, the vector can be expressed as a gradient of a scalar function phi. That is called a potential function. For a rotational region of flow, v vector equal to del operator vector phi. The u is given by tau by tau x, v equal to tau pi by tau y, then w equal to tau pi by tau z. Particularly rotational regions flow, del square pi equal to 0. The del square is nothing but tau square by tau x plus then I vector plus tau square by tau y square j vector plus k vector into tau square by tau z square. So yeah, the first gate question is, a two-dimensional frictionless flow field is given by velocity vector x I vector minus y j vector. The expression for the pressure gradient at any point in the flow field is what? That is a question asked here. The v vector is u vector, that is the I vector quantity is u, then j vector quantity is small v, that is the velocity in y direction, velocity in x direction. The Eulerian equation is dou u by dou t, the continuity equation in the x and y direction. X direction dou u by dou t, u dou u by dou x plus b dou u by dou y plus w dou u by dou z as equivalent to the body forces in the particular x direction minus 1 by rho dou p by dou x. Similarly, if you are writing the continuity Euler's equation for the y direction, you have a dou v by dou t plus u dou v by dou x plus b dou v by dou y plus w dou v by dou z, that's equal to 40 forces along the y direction minus 1 by rho into dou p by dou y. This is a pressure gradient we have to find. So for an normal conditions, there is no extra forces or body forces acting in the sense this quantity become 0. So this equation is, the normal equation comes as dou u by dou t plus u, dou u by dou x plus v, dou u by dou y plus omega, that is w, dou u by dou z equal to minus 1 by rho dou p by dou x. So here the velocity is given, velocity vector equal to x I vector minus y j vector. So this is nothing but u I vector plus b j vector. U equal to x, b equal to minus y. So if you are getting a dou u by dou x is equal to 1, dou v by dou y is equal to minus 1. There is no possibility of dou u by dou y. So dou u by dou y equal to 0. Similarly, dou v by dou x equal to 0, because there is no x term in the v velocity. Similarly, there is no y term in the u velocity. So this is the difference. So in this one, and the time derivative is not available, so that's 0. Then you have an u, dou u by dou x, that's equal to x into 1. Then dou u by dou u by dou y equal to 0, so this term is 0. Then this is already 0, so you can get x equal to minus 1 by rho dou p by dou x. Otherwise, dou p by dou x equal to minus rho x. Similarly, if you're going for an y equations, here the same thing, dou v by dou t. This quantity is 0 for a y direction. Then here you have an dou v by dou x. So as dou v by dou t plus u dou v by dou x plus v dou v by dou y plus w dou v by dou z is equal to the body forces in y direction, that's also 0, minus 1 by rho dou p by dou x. So here this is 0. This is 0. Dou v by dou x equal to already 0. So v equal to minus y. Then dou v by dou y equal to minus 1. Then plus, you have to leave it. This quantity is already 0. So that's equal to minus 1 by rho dou p by dou x. Otherwise, say dou p by dou y here. Dou p by dou y. So dou p by dou y equal to the minus into minus plus. Then here you have a 1 minus. So minus rho y. So in the vector form, if you are adding the pressure gradient, dou p by dou x plus dou p by dou y is giving minus rho x I vector then minus rho y j vector or minus rho on the outside. You can get an x I vector plus y j vector. This is the answer for the particular question. Water flows through a pipe with a velocity given by v vector equal to 4 by t plus x plus y in the j vector, unit vector, meter per second. But j is unit vector in the y direction, t is greater than 0 in seconds, x and y are meters. The magnitude of total acceleration at the point x, y, that's 1, 1, and t equal to 2 seconds is what? That's the question asked. Here the total acceleration. The acceleration is dependent on x, y, z, and time. That derivative is known, that's equal to a x comma a suffix x, y, z, t, that's equal to dou v vector by dou t, that's a local acceleration, then a convective or advective acceleration. I have to find out that particular each component of the local and convective acceleration values. Substitute in that one acceleration equation, we can find the value. Well as acceleration is x, y, z at t as equal to t v vector by dt plus u into t v vector by dx plus v into t v vector by dy plus w into d vector d v vector by dz. That's an acceleration, total acceleration here. The given velocity vector field equal to 4 by t plus x plus y in jth component, meter per second. So here, this is the velocity of v, because it's not j, it's not j unit vector, so this representing the velocity at y direction, that is small v. Now what about that u value and w value, then time derivatives? That is not given. So this value is 0. Then this also a 0. So we can omit this 2. The remaining vector is t. So d vector t v vector by dt equal to 1. If you are differentiating this one, the t parameters here only. So t vector by dt is given by minus 4 t square. That is the v vector for a particular one is 4t minus 1 plus x plus y. So dv by differentiating with respect to time, you can get this a constant is a 0. So here you have a minus 1 into 4 t minus 1 minus 1. You can get dv vector by dt equal to minus 4 t minus 2. Otherwise, dv by dt equal to minus 4 by t square. Then the remaining values you can find v vector is 4 by t plus the v is given 4 by t plus x plus y. That's not b. This value is not 0. Then differentiating with respect to y, you have to differentiate with respect to y. In that one, you have a value of only 1. That is, the parameter is y equal to, and this one, t is a constant, x is a constant, then you can get dv vector by dy equal to 1. That is differentiation of only y terms, you can get dy by dy. That's one value. Then already other terms of 0. We can substitute these values in the initial equation. We can get this become dv vector by dt is nothing but minus 4t square plus the b vector v equal to v 4 by t plus x plus y dv vector by dy equal to 1. So you can get minus 4, that is the same thing will come because the multiplication is 1. There is no subtraction or adding because everything is in a unique algebraic terms. So I have to apply the point condition, position condition. The position is given as 1, the time is 2, t equal to 2, then x equal to 1, y equal to 1. So the a of x comma y comma h at t equal to minus 4 divided by 2 square plus 4 by 2 plus 1 plus 1 is equal to minus 1 plus 2 plus 1 plus 1. You're getting 3 meter per second square. This is my acceleration, so that value is in second square, meter per second square. For a two-dimensional incompressible flow field that is given by u vector equal to a into xi vector minus yj vector, where a is greater than 0. Which one of the following statement is false? So I have to check that statement. It satisfies continuity equations. Here the velocity vector is given, the velocity vector having a x velocity and y velocity. The a is some constant like the parameter that is greater than 0. So I have to check the continuity equation, either it's satisfying or not. We can say either it's a true or false. Similarly, it's a unidirection when x tends to 0 and y tends to infinity. Definitely unidirectional. One is become an infinity, another one is tends to 0. It's not unidirectional. This is a true statement. Then its streamlines are given by x equal to y. The streamline function is known. I have to check using this one. I have to check that one and finding either the relation between x and y is x equal to y or x by y or x y equal to something. You have to check. It is an irrotational. For irrotational condition, you have a formula. You have to check that either this thing is satisfying the irrotational condition or not. The given vector Yes, v vector equal to a into xi vector minus yj. For a two-dimensional thing, this is a u, this is a p. The first condition, continuity. That is dou u by dou x plus dou v by dou ez for a two-dimensional is equal to 0. So from this, dou u by dou x equal to 1 and dou v by dou y equal to minus 1. Because here u equal to x, v equal to minus y. So we are substituting here, the continuity equation is satisfied. So the first option is true, that is not a false. The second one already we said is not unidirectional for a particular condition. The third one is streamline function. For a streamline condition, we have a dy by dx equal to v by u. Here the v equal to minus y, u equal to x. And if you are separating this thing in a variable separable method, you have a dy by y combining this with this equal to dx by x. If you are integrating, you can get ln y equal to natural logarithmic of x plus minus plus some constant. Otherwise, there's a ln x plus ln y equal to some constant. So, if you're taking the anti-lag, xy equal to some constant, but the given condition is x equal to y. So, this is false statement. That is x equal to y is false statement. Then the irrotational. Suppose the option is in the order, it may come first in the sense we have to check for a irrotational condition. In the xy plane, you have to find out the irrotationals. In that one, you have to 1 by 2, 1 by 2, 1 by 2 dou v by dou x minus dou u by dou y. It's a constant, you can take out. Then the remaining dou v by dou x. So in the v term, there is no x quantity. So dou v by dou x equal to 0. Similarly, in the u, dou u by dou y, that's equal to 0. So this equal to 0 as a irrotational. The rotational common is 0, so there's an irrotational. That condition also have to check. Suppose the option is given in different order, you have to check 1 by 1. In a Lagrangian system, the position of a fluid particle in a flow is described as x equal to x naught, that is x suffix naught e power minus kt, and y equal to y naught e power kt, where t is the time while x naught, y naught and k are constants. The flow is, what type of flow you have to find out, either unsteady, one dimensional, a steady, two-dimensional, or steady one-dimensional, or unsteady two-dimensionals. For a steady and dimensional conditions, I have to check the dependency using the velocity parameters. So I have to go for an x and y. Flow is described by x and y. So I have to find out the velocity. Finally finding the velocity in terms of either what parameters. Based on that one, either it's steady or a two-dimensional or one-dimensional, we can conclude. So the given is x equal to x naught e power minus kt, y equal to y naught e power kt. So from that, we can get the u equal to nothing but dx by dt as equal to minus k x naught. If you are differentiating this one, you can get x naught e power minus kt. Similarly, the y directional velocity is given by dy by dt as equal to, if you're differentiating this thing, you can get plus k into y naught e power kt. So the velocity vector, total velocity vector is given by a ui vector plus vj vector plus vk vector. So here the given values, w is not existing, so it's a 0, 0. So remaining thing existing is u and v, so there's a two-dimensional. So the v vector is given by, so there's nothing but minus k into x. This is nothing but, because x naught e power kt is nothing but the given starting given value. Similarly, this is nothing but this quantity y. So v equal to k into y. So if you are writing in the vectorial notations, e equal to minus k xi vector plus k y j vector. If you take now k in the outside in the sense, minus k in the sense, we can xi vector minus y j vector. This is depending on x and y space coordinate opposition vector, not depending on time. So already it's a two-dimensional, it's a time independent, so it's called steady flow. Steady flow. The divergence of the vector field is given by u vector equal to e power x cos yi vector plus sin y j vector. So I have to find out the divergence of the vector field. Divergence of the vector field is nothing but del operator dot this particular vector, that is I dou by dou x plus j dou by dou y plus k dou by dou z into dot vector of this quantity. We can get some values. You can check it with the given option. Divergence of vector equal to del vector dot u vector, that is I dou by dou x plus j dou by dou y plus k dou by dou z into the given vector. The given vector is e power x cos yi vector plus e power x sin y j vector. In the dot product, so here this quantity is not available, so you have to multiply the I component, then you can get I1, then dou by dou x of e power x cos y plus dou by dou y of the j 1. So dou by dou y of e power x sin y. So the value equal to dou by dou x of e power x equal to e power x cos y. So here cos y plus, if you're differentiating this thing with y, e power x is a constant, then dou sin y by dou y equal to cos y. So you have a 2 e power x cos y. That is the divergence of u vector. Consider the two-dimensional velocity field given by velocity vector equal to 5 plus a1 x1 x plus b1 y I vector plus 4 plus a2 x plus b2 y j vector, where a1, a2, b2, b1 are constant. Which of the following conditions need to be satisfied for the flow to be incompressible? For incompressible things, divergence of vector equal to 0. So I have to find out the divergence of the vector. Then you can have some relations among these four. So the given vectors are 5 plus a1x plus b1y I vector plus 4 plus a2x plus b2y j vector. So the divergence of v vector equal to 0 for incompressible flow. For an incompressible flow, this condition must be satisfied. So this is nothing but I dou by dou x plus j dou by dou y plus k dou by dou z. Then if you're multiplying this divergence with a velocity vector, the I vector you have I into I1, so you have only the divergence of vector is given by dou by dou x of 5 plus a1x plus b1y, then plus the k is not available, k is not there, so this becomes 0. Then j vector, that is 1. The remaining thing is dou by dou y into 4 plus a2x plus b2y is equal to 0. That is the condition for an incompressible thing. So if you are differentiating this one, this constant 0, then differentiating partial differentiation with respect to x, this quantity is 0, so you can get a1. Then plus, if you are differentiating with this, there's a constant 0, then differentiating with respect to y, this quantity becomes 0, so you can get b2. So a1 plus b2 equal to 0 for incompressible conditions. For a steady flow velocity field given by v vector equal to minus x square plus 3y I vector plus 2xy j vector. The magnitude of acceleration of a particle at 1 comma minus 1 is in dash meter per second square. So you have to go for an acceleration equation. An acceleration equation you have to find out ax and ay. It's only in the two dimensions. That is u value and v value is given. X directional velocity, y directional velocity. So you have to find out the x directional acceleration, y directional acceleration. Then I have to find the magnitude of the acceleration. So the given vector v vector equal to minus x square minus x square plus 3y as an I component plus 2xy j component. So from that u equal to minus x square plus 3y and b equal to 2xy. The common ax is given by u dou u by dou x plus b dou u by dou y. Similarly, a acceleration in y direction is given by u dou v by dou x and b dou v by dou y. So I have to find out the terms to apply in the acceleration. So dou u by dou x equal to, if you are differentiating, you can get minus 2x. Similarly, dou u by dou y is equal to 3. Here the v, dou v by dou x equal to 2y, dou v by dou y equal to 2x. So all the components required for x acceleration and y acceleration is arrived. So the x equal to u equal to minus x square plus 3y into dou u by dou x is minus 2x plus b equal to 2xy and dou u by dou y that's equal to 3. So that's given by minus 2x cube, so 2x cube minus 6xy plus this is 6xy. So that final value is minus 2x cube. It's cancelled. Similarly, ay is given by u minus x square plus 3y dou v by dou x, dou v by dou x is 2 plus v equal to 2xy dou v by dou x equal to 2x. This value is represented. is equal to minus 2x square y plus 6y square plus 4x square y. Final answer is 2x square y plus 6y square. And if you are substituting the x and y value 1 comma minus 1 here, substituting this 1 comma 1, ax equal to minus 2 into 1 cube minus 2 minus 2. So here this is now plus, minus into minus plus. So this value is now plus 2 values. And if you are substituting in the y component, you can have a 2 into 1 square minus 1 plus 6 into minus 1 the square. You have minus 2 plus 6, that is 4. So the a is given by ax square plus ay square under the root is 4 plus 16 under the root, so 20. Then I have to check this 20 with the answer. The answer is not exactly root 20. You have to formulate 4 into 5 under the root as equal to 2 into root 5. This is the answer given in the question. For the vector b equal to 2yz I vector plus 3xz j vector plus 4xy k vector, the value of Taylor vector, that is divergence of curl, there is a cross product, there is the scalar product, dot product, then the cross product of the vector equal to what? By the vector identities. Vector identities, divergence of curl of any vector equal to 0. That is, the answer is 0. Then the next question is the divergence of the vector b equal to minus, that is vector b equal to minus y I vector plus x j vector is 1. So here the divergence is asked, the divergence is divergence vector dot then v vector, the cross product will be removed, the remaining things. The meaning of the divergence, that is divergence is I vector dou by dou x. I vector not having any x component, x parameter. So dou by dou x of this quantity, this will be treated as a constant, so this is become 0. Similarly, in the div means I dou by dou x plus j dou by dou y plus k dou by dou z. So the I, you have a partial differentiation of dou by dou x, but in the I given with velocity vector, I is not having any x. Similarly, for a j in the divergence you have only dou by dou y, but in the given velocity vector there is no y value, so the divergence of the given vector is 0. The next question is the velocity component in the x and y direction of a two-dimensional potential flow are u and v respectively. Then dou u by dou x is equal to what? For a potential flow, you have a correlations. The correlation will be used to find out the relation between dou u by dou x. For a potential flow, it must satisfy the continuity equations. So the continuity equation for a two-dimensional is, we know that dou u by dou x plus dou v by dou y is equal to 0. So if you are rearranging this, dou u by dou x equal to minus dou v by dou v by dou y. There's a relation you have, that is dou u by dou x is already given, dou u by dou x is given, so the answer is minus dou v by dou y is equal to, this is equal to minus dou v by dou y. A leaf is caught in a whirlpool. At a given instant, the leaf is at a distance of 120 meter. That's away from the whirlpool center is, that is 120 meter from the center. The whirlpool can be described by the following velocity distribution: the radial velocity and the angular velocity. This Vr equal to minus 60 into 10 to the power of 3 pi divided by 2 pi r meter per second. V theta equal to 300 into 10 to the power of 3 2 pi r meter per second. R is in meter, is the distance from the center of the whirlpool. So here from 120 meter towards the center, so R value is comes on decreasing. What will be the distance of the leaf from the center when it has moved through a half a revolution? That is, the leaf is just gone a half revolution. The half revolution is 180 degree or pi radian. Okay. At the time, at what distance the leaf will be? That is a question. The option is given. So I have to go for a correlations between this angular velocity as well as the radial velocity. Then I have to separate the variables, that is r variables and theta variables. That the r is varying from 120 to some particular distance. The distance you have to find out, but theta is from 0 to pi. So I have to use that values in the calculation. The Vr is given as minus 60 into 10 to the power of 3 by 2 pi r. Then V theta is given as 300 into 10 to the power of 3 divided by 2 pi r. So if Vr divided by V theta, that is radial velocity divided by angular velocity, is given by minus 60 into 10 to the power of 3 divided by 2 pi r 2 pi r into divided by this quantity. So 2 pi r will be in the numerator, divided by 300 into 10 to the power of 3. This will be cancelled. This will be cancelled. Then here 0 is equal to minus 1 by 5 r. The radial velocity equal to minus 1 by 5 times of v suffix theta. We know that Vr equal to dr by dt. Similarly, the angular velocity v theta equal to r omega r into d theta by dt. So if you are substituting these things in this correlations, you have a dr by dt as equal to minus 1 by 5 r into d theta by dt. So the dt will be cancelled. If you are separating the variables, we can get dr by r as equal to minus 1 by 5 d theta. So we know that condition of the leaf is from 120 meter to some r distance. The r distance is not known, so we have to find out. Then at the same time, for that condition, the theta is 0 to 180 degree is equal to pi. So if you are integrating this thing, the distance parameter, you have integral 120 to r dr by r as equal to minus 1 by 5 d integral d theta. The limit is 0 to pi. That's equal to ln r as equal to minus 1 by 5 theta 0 to pi. Otherwise, ln r equal to ln r over the limit 122 r equal to minus 1 by 5 pi. That is the one. So here ln r by 120 is equal to minus pi by 5. So if you are taking a angle arc, r by 120 equal to e power minus pi by 5. That's equal to e power minus pi by 5 equal to 0.533. So that r equal to 120 into 0.533 is approximately 64 meter. That is above 50%, 60, then 0.033. If you're multiplying, you can get 3.8. So 63.8 or 9, 63.9 meter it may come. So the value at a distance for an half revolution, it will be moved to a position of 64 meter. In a two-dimensional velocity field, the velocities u and v along the x and y directions respectively. The convective acceleration along the x direction is given by, already the acceleration parameter is given by for particular terms in the x direction, in the sense the x direction velocity with respect to rate of change of x direction velocity with respect to time, that is giving a local acceleration. The remaining terms are advective or a convective acceleration. So the remaining term is the particular velocity, the x directional velocity, then the particular x directional derivative for the x directional velocity plus y directional velocity, then x directional velocity with respect to y derivatives, that is dou y. So that ax is given by dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w into dou u by dou ez. That is an x direction acceleration. So for a two-dimensional, the terms plus W dou U by dou Z is 0. So the C is the answer. There's one question I got from a GATE question paper. That is, some data is missing. It's not possible to find it. That is, for a streamline, you have a calculation of x and y values, the u values and v values will be given in terms of x and y. You can correlate the x and y like in a constant or a x, y square is a constant. You can find it using the streamline functions. So already we have seen one question the same type, that is the finding true or false the following statement. They are giving x equal to y. We found that x equal to xy equal to constant. Like that you can find out that the value is given, you can find out. For the continuity equation given by divergent b equal to 0 to be valid, where b is the velocity vector, which one of the following is a necessary condition. So this is a divergence of vector equal to 0 in the sense that's an incompressible flow. Here you are asked to evaluate asserted field flows for the suitability in a given laboratory application. The following three choices expressed in terms of the two-dimensional velocity fields like xy plane are made available. So the P is one type of fluid flow, another Q is another type of fluid flow, R is another type of fluid flow. That P having a U velocity and V velocity is given. Similarly, Q is having a U and V velocity that is given, R also given. Which flow should be recommended when the application, the laboratory, the application requires the flow to be incompressible and irrotational? So for all three fluids, you have to check either it's incompressible or irrotational. Both the conditions you have to check using the formula, irrotational formula and compressibility formula. You have to, for incompressible flow field, that is incompressible in the sense continuity equation must be satisfied. The given having a only two-dimensional, so dou u by dou x plus dou v by dou y equal to 0. So the continuity equation must satisfy for an incompressible flow. Similarly, irrotational thing, zeta z equal to 1 by 2 dou v by dou x minus dou u by dou y. That value is satisfied. That is, here this value equal to 0, that is a irrotational. Suppose if it is a value, is a rotational. Here also it is a value in the sense is not complied with the continuity equation. So you have to check these two conditions for P, Q, R, that is three different types of fluids. For P, the U value is 2y, V equal to minus 3x. So the dou U by dou x equal to 0, dou U by dou y equal to 2. Here dou V by dou x equal to minus 3, dou V by dou y equal to 0. So the continuity equation, the first one is a continuity equation, second one is a vorticity vector, cortex but verticity vector. So here the continuity equation dou u by dou x plus dou v by dou y that's equal to 0. If you are adding these two, we can get 0. So it's incompressible. Incompressible. So this value is satisfied. The first condition is satisfied. The second one is zeta is equal to dou v by dou x. Dou v by dou x is minus 3. Minus 3 minus dou u by dou y equal to minus 2. So if you are considering these two subtraction, you can get minus 5. So this is a rotational flow. As a rotational flow. So the R is not applicable to the laboratory conditions. Then I have to go for a Q fluid. Q fluid U is given by 3xy and B equal to 0. So we have to go for a dou U by dou x equal to 3y, dou U by dou y equal to 3x. Then the other terms here, whatever the things you are differentiating, is equal to 0. So dou u by dou x plus some value, because 0, this has a value. So this is not compressible. Then rotational conditions, if you are considering this has some value. So this is a compressible as well as the rotational flow. The Q is compressible as well as the rotational flow. So this is not applicable for a laboratory, the given laboratory purpose. So the remaining fluid is R. So if you are fine, check P and Q. So you can blindly select R unless otherwise, if the fourth answer is none of the above. Okay, so this value I have to check. So the R equal to U value is given by minus 2x and B value is given by 2y. So dou U by dou x equal to minus 2, dou U by dou y equal to 0, dou V by dou x equal to 0, dou B by dou y equal to 2. So if you are considering the continuity equation, that is continuity equation here, summation of dou U by dou x plus dou V by dou y is equal to 0. Minus 2 plus 2 is a 0. So it incompressible. Then the rotational condition dou V x minus dou U by dou y. So this condition also 0, that is a rotational. Rotationals. So for the given laboratory condition requirement, the fluid R is the applicable one. The velocity vector of a flow field is given by V equal to 2xy I vector minus x square z j vector. The vorticity vector at 1 1 1 is what? The vorticity vector at 1 1 1 is what? The vorticity vector that is having ijk, the determinant of ijk, dou by dou x, dou by dou y, dou by dou z, then uvw. So if you are getting a determinant that is a vorticity vector. The vorticity vector I j k dou by dou x, dou by dou y, dou by dou z. Here u v w. From the given velocity vector minus 2xy I vector minus x square z j vector. This u, this v. So here minus 2xy minus 2xy. Suppose the problem given is plus, you can take the plus value. I hope this value is plus, the given vector is plus 2xy. Then the v vector equal to minus x square z. Then z, w vector is 0. If you are doing this work, I equal to, you have to left the I column, then cross multiply the j and k column. You have dou by dou y of w. W is 0, so that value is 0. Then minus dou by dou z of v. V is x square minus x square z. As dou by dou z of minus x square z. That's I vector plus minus j vector into the jth column will be left over. Then I have to multiply the I k column. Dou by dou x of w is 0. Then minus dou by dou z of this quantity. So dou by dou z of 2xy plus k vector of the kth column is left over, ij will be multiplied. So dou by dou x dou by dou x of minus x square z minus dou by dou y of 2xy. So this is the vorticity vector. Here the I vector, if you are differentiating this, you can get minus of, here you have one more minus, that will be plus 2x z, differentiating with respect to z, you can get minus into minus, that's not x square, then minus j into, if you are differentiating with respect to z, There's a constant, so this 0. So the jth quantity is 0 plus k. The k value is, if you are differentiating with respect to x, you can get minus 2x z minus, if you are differentiating with respect to y, you can get minus 2x. And the point is given. You have to find out the vorticity vector at 1 comma 1 comma 1. If you are substituting that, the vorticity vector will be equal to I, x square is 1 square, then plus k into all x, y, z is 1 minus 2 into 1 into 1 minus 2 into 1. So the vorticity vector equal to I, here minus 2, here minus 2, minus 2, minus 2, minus 4k. That's now vorticity vector given in that one. That's an answer given as I minus 4k. The problem given is b equal to 2xy. So minus is not there. Here initially took minus. So the correct equation is taken and the answer is I minus 4k. Streamlined and equipotential line in a flow field is either parallel or perpendicular or intersect at an acute angle or identical. So I have a relation for a streamline and equipotential line in terms of u and b. I have to relate that one with, I have to relate that equipotential line and stream functions. The equipotential line dy by dx is given by minus u by b. This is now slope. This is now m1 in the potential line on a slope. Then the dy by dx for a streamline equal to b by u. This is now slope m2. If you're multiplying, that is the product of the two slopes m1 and m2 equal to minus u by b into b by u as equal to minus 1. So this condition represents a perpendicular conditions. So this value present the u and b is vice versa. So we can get in the minus 1. That is the multiplication factors. So for the given condition, they are perpendicular to each other. A flow field which has only convective acceleration. So the local and convective or advective acceleration in the any of the acceleration component. The ax is given by dou u by dou t plus u plus dou u by dou x plus v into dou u by dou y, like that you have our values. In that one, other than the local acceleration, remaining are convective, that is based on the space, that is position x derivatives, y derivative, z derivatives. That is the condition in the particular space marching. That is having in the sense that have any value in the sense that's represent a non-uniform flow. Only having a convective in the sense the dou u by dou t is, or dou v by dou t is, or dou w by dou t is 0. That is 0 in the sense as a steady condition. Steady condition, then only convective acceleration is available. That's a non-uniform fluid. So with that one, we can wind up this fourth session of this gate coaching. We can say that next class in the Bernoulli based problems. Thank you.